9.5, dilations. This is our fourth transformation. We have done translations, reflections, and rotations, and now we're doing dilations. To do dilations, we are going to use a scale factor to make a larger or smaller copy of a figure that is similar to the original figure. Okay, all of the ones we've done so far have been isometries, which means they are congruent to the original figure. These are simply similar, which means they are proportional, and that's where the scale factor comes in. So these are proportional to the original figure by said scale factor. All right, let's see. A dilation with center C, okay, that's we recognize that, and scale factor n, so n is our scale factor, where n is greater than 0. None of our dilations are going to have negative scale factors. Okay, has two properties. The first one we recognize, the image of C, right, that's our center, is itself. That means that C, if it's on the center, if your point is the center, if it's on the center, that it just stays there. C becomes C prime. All right, for any other point, R prime is on ray CR. Okay, let's find that. So we have our center here at C. If you are point C, then you simply become C prime. If you are not on point C, then we have this ray CR, right? This ray goes out like that. And R prime, so we take point R, and R prime, our image, is somewhere on this ray. And the length from C to R prime, right, that's what that says, is n times the length of CR. And remember, n is our scale factor. So we're going to put a box around this big red box. Now, what does this mean? I guess we could underline this. Your image is similar, right? We've already said that that's a proportional by a scale factor. Let's look and see how this works. So this is going to be our scale factor here. This is our scale. Scale. It's kind of messy. All right, let's look at some vocabulary. An enlargement, your dilation is an enlargement. That means it gets bigger, right? If your scale factor is greater than 1. So that makes sense. We're making something 2 times bigger, or 3 times bigger, or 5.7 times bigger. Your dilation is a reduction if your scale factor is between 0 and 1. This means that it's a fraction. And this makes sense. You reduce something if you are making it half as large, or 0.375 times as large. So let's look at these examples here. We have center at A of figure ABCD, and we want to enlarge it. Our scale factor is 2. What that tells us is that if we measure the length of, say, AD, let's start here, A is on the center, so A maps to itself, becomes A prime. But let's look at point D now. So we draw a line, draw a ray through AD, and then we measure length AD, and then we multiply that times 2. And then we measure length. We measure 2 times out here, and we get D prime. This is 2 times length AD. And then we do that for the next point. We take point B, and we draw our ray. And then we measure length AB. And then we multiply that by 2, and we get point B prime. And the length from A to B prime is 2 times the length of AB. And you guessed it, we do that for our third point here, C. We draw a ray through C, and we measure the length from A to C, and then we multiply that by 2, and we measure out here to C prime, and this length is 2 times AC. So that's easy enough. All we need is a ruler to do these. All right, let's look at a reduction. We have our pre-image quadrilateral EFGH, and we are using a scale factor of 1/4. And so we find our center C. There are no points on our center, so nobody maps to itself. And then we pick a point. Let's pick point E. We draw a ray through point E. And then we measure the distance from C to E. And then we divide that distance by 4, or we multiply by 1/4. And then we measure that distance, and it becomes E prime. This distance here is 1/4 times CE. Okay, we can do it one more time here. Let's do H. We draw a ray, CH. And then we have our point H, our pre-image H, and then we measure the distance from C to H, and then we multiply that by 1/4 of CH, and we measure that distance and we get H prime. So you see how an enlargement, you multiply and you get a longer line. A reduction, you multiply and you get a shorter line. And we would continue to do that for points F and G, but I think you get the point here. Now, how do we use this information to find a scale factor? All right, we have triangle X prime, T prime, R prime is a dilation image of triangle XTR. The center of dilation is at X. You know, I like to mark my center so I know where I'm working from. Is the dilation an enlargement or a reduction? What is the scale factor? So are we enlarging or reducing? Well, our pre-image is smaller than our image. So we are going to say, because the image is larger than the pre-image, this is an enlargement. So how do we find our scale factor? Well, just like we have found our scale factor in every chapter we've done this since. Okay, how do we find a scale factor? We compare the lengths of the corresponding sides. Now, something I want you to be careful of here. Sometimes, I think we should redraw things. There's our pre-image, and then we could just draw our image, right? And where are our corresponding sides? Well, it's this diagonal one over here. We know this measures 4, but how long is this one over here? Be careful, It's not 8, it's 8 plus 4, because this part right here counts as well. So it is 12. Well, how do we find our scale factor? We just do our corresponding sides. N, our scale factor is always image over pre-image. Okay, we want to remember that. We probably should have written that up at the beginning. Your scale factor is always image over pre-image. So what is our image length? That is 12. What is our pre-image length? That is 4. So our scale is a 3-to-1 scale. It's an enlargement with a scale factor of 3-to-1. Scale factor of 3. All right, go ahead, and before we do that, I really feel the need to go back up here to the top and say that N is always your image value over your pre-image value. I feel better. Hope you do too. It's important information. All right, now go ahead and pause the video and do the next problem. Okay, this says quadrilateral J prime, K prime, L prime, M prime is a dilation image of quadrilateral JKLM. The center of dilation is at O. First thing I did was mark that. No, come back. First thing I did was mark that at O. Okay, is the dilation an enlargement or a reduction? And find the scale factor. So your image is smaller, so it is a reduction. The pre-image is bigger, the image is smaller, so it's a reduction. And then to find the scale factor, we know that the scale factor equals image over pre-image. And so lucky for us, we had a vertical line here, and so I compared the length of OJ prime to OJ, and they were easy to count, 1 to 2. And we have a horizontal line here, and so I compared the length of OK prime to the length of OK, and again got 1 to 2. But what happens if we don't have horizontal and vertical lines? Those would be enough. You go, well, if we're told that it's a dilation, 1 is probably enough, 2 confirms it, but we wanted to go a little further and be sure, so I drew line OL, and I compared that to OL prime. And we know how to use the distance formula. I found my points, wrote my distance formula, and I got the square root of 13 over the square root of 52. Well, how do we know what ratio that is? Well, we simplify our radical. 52 is simply the square root of 4 times the square root of 13. I had an idea it might be, so that was some of the first numbers I chose. And my square root of 13 cancels, and I get 1 to 2. And so, yes, definitely our scale factor is 1 to 2. We have a reduction with a scale of 1/2. Our image is 1/2 of the original. All right, well, that was fun. We do enjoy distance formula. All right. let's see. We looked at a dilation figure in the coordinate plane. This is probably important. In this book, all dilation figures in the coordinate plane have the origin as the center of dilation. So that makes things really easy. So we are going to have a dilation formula here. Remember when we wrote translation formulas, the translation equation? We have a dilation formula, and for translations, we added, remember we did x plus 2, y minus 3, because we moved over 2 places and down 3 places. Well, how do we do dilations? We do dilations by multiplying. So if we multiply our coordinates of P by our scale factor, we end up with our dilation equation here. So the point P at xy maps to P prime at nx and ny, right? N is our scale factor. So let's take a look at an example of this. Finding a dilation image. What are the images of the vertices of triangle PZG for a dilation with a center 0, 0, yay, let's mark that, and a scale factor of 2? And then graph that image. So we could use our distance formula, because that's fun, but we like shortcuts. And formulas tend to just be shortcuts. So we identify the coordinates of all of our vertices. So P here is at over 2, 0. Z here is at negative 3, 1. And G here is at 0, negative 2. And we know we have a scale factor of 2. So we simply take all of our coordinates and we multiply everybody by 2. 2 times 2, 2 times 0. 2 times negative 3, 2 times 1. 2 times 0, 2 times negative 2. And we get our image coordinates. And then we could plot those. P prime is at 4, 0. Z prime is at negative 6, 2. And G prime is at 0, negative 4, which makes sense, right? Because our center of dilation is right here. Our ray OG would go straight down the y-axis, and our ray OP goes straight down the x-axis, and our ray OZ goes at some slope here, which we don't have to worry about anymore. But you can see how it goes through there. So that's super easy. All right, it looks like you have a next problem to solve. Let's give ourselves a little space here. Pause the video, try the next problem. All right, number 2 says, what are the images of the vertices of our original triangle with a center at 0, 0 and a scale factor of 1/2? Okay, so we simply take our points, our pre-image points, we multiply our coordinates by 1/2, and we get our image coordinates. P prime's at 1, 0, Z prime negative 3 over 2, negative 3/2, comma 1/2. You could write those as negative 1.5 and 0.5. Those are easier to graph that way if you like. And G prime is at 0, negative 1. And part B, I have a feeling you just waited for me to answer this one and you didn't go back to chapter 7. All right. How can you prove that your triangles are similar using a postulate or theorem from chapter 7? Did you actually go back and look at your postulates or theorems from chapter 7? because if you had, or if you did, I bet you would see immediately how to do this. We use the distance formula. We find that our side lengths are proportional, and we use the side-side-side similarity postulate. Okay, let's look at our last example here. This says real-world problems, such as things that we see through a microscope, that would be an enlargement, or things that we see on our computer screen, that would be a reduction. So how do we use scale factor to find a length? If a magnifying glass shows you an image of an apple seed, so the magnifying glass shows you the image of the apple seed. Image is important, right? Then we know that that's the second one, not the original. That is 7 times, I see a scale right there, the object's actual size. So our scale factor, we know this is an enlargement because our apple seed is much bigger. N is positive, so that is an enlargement. The scale factor is 7. What is the actual length of the apple seed? Well, here is a formula that you should mark, put stars around, flashing neon, that's almost a star. Image length equals scale factor times actual length. Image length is our prime. This is exactly what we just did with our coordinates, right? P prime was n times x, n times y. Your image length is your scale factor times your actual length. This is pre-image. All right, so we just put in, we know that apparently we know that the image is 1.75 inches or something. I don't know, it seems we were missing some information here. Apparently our image is 1.75 inches. We'll call it inches. We know our scale factor is 7. We want to know the actual length of the seed. We simply divide both sides by 7, and it is inches. The actual length of the apple seed is 0.25 inches. All right, why don't you try the last problem here? Hopefully you have enough information. Okay, this one tried to be a little tricky with its wording. We're told the height of the document on our computer screen is 20.4 centimeters. Better fix my answer. There we go. It's 20.4 centimeters. When we change the zoom setting, now zoom makes you think you get bigger, but it says change your zoom screen from 100%, so this is at 100% here, to 25%, so we are getting smaller. We know we have a reduction. The new image of your document has a scale factor of 0.25. So I wrote all this down. I have a reduction. My scale factor is a fraction. Decimals and fractions are the same thing. It's a fraction, so that's good. I know it's a reduction. I know that my actual, or my pre-image, is the height is 20.4 centimeters, and I want to find the height of the new image. So I'm going to call that x. And I use my fancy equation from just up above. Image equals scale times actual. Image is what I want. My scale is 0.25. My actual is 20.4. Just multiply it out. And my image height is 5.1. So I think dilations are some of the easier ones to do. If you have to, use your ruler. If you're doing them by hand, use your ruler. Otherwise, we have some very handy formulas. We have our dilation formula, the nx, ny for our coordinate planes, and we have the formula we just have here, image length equals scale factor times actual length. So work carefully, think about your scale factor, and I think these are kind of fun. I hope you do too.